Hello chemists, this is Ms. Placino and you're watching lesson 12.6 on titrations and indicators. In today's lesson we're going to talk about how we can experimentally determine when a solution has been neutralized. So we're going to be covering a pretty important lab technique with titrations. Goals for today's lesson. You should be able to explain what a titration is and how it is used in a lab. You'll be able to determine the concentration of an unknown acidic or basic solution. And we're going to interpret titration curves and choose an appropriate indicator. That second one is really the big one for today. We've got some calculations to perform, so make sure you've got a calculator ready to go. Let's get started. Today's lesson is really going to build on what we talked about in the previous lesson with neutralization reactions. So just to review, we know that if you take an acid and you react it with a base, again, we're really talking areneous acids and bases, you're going to produce an ionic compound, more commonly called a salt, and water. It's that reaction from the H+ of the acid and the OH- of the base to create water that's our neutralization. We know that the identity of the salt really depends on which acids and bases have been used to neutralize one another. So we can run this reaction in the lab. And we do that with a technique called titration. With titration, we use an Erlenmeyer flask. And you can't see the rest of it, but we'll demo it in class. You've got this kind of long skinny tube called a burette with this little valve at the end of it. So it's going to allow us to deliver very specific and precisely measured volumes of our acid or base. So this is just a technique that is used to determine the concentration of an unknown acid or base through our neutralization reaction. And you might be able to tell as you look at that picture that looks like a little bit like it's got a color to it. It's kind of pinkish. Most of our acids and bases tend to just form completely clear solutions. Like you wouldn't know that something had been dissolved in the water unless you tried to run a test on it. We add something called an indicator when we perform a titration to kind of let us know when to stop reacting the acid and the base. There are many different indicators that chemists can use in the lab. We're going to talk about a handful of them for our class. Basically, an indicator is just a weak acid or base, and then it's going to change colors at different pH levels. So what we have in this picture here is an indicator called phenolphthalein. Phenolphthalein in an acidic solution is clear. And in a basic solution, it's going to turn this pink color. And it's that change of color that would indicate or kind of signal to the chemist running the experiment that it is time to stop the titration. When it turns colors, we call it the endpoint, and it's supposed to coincide with the equivalence point, which is where the H+ and OH- ion concentrations are equal. We're going to kind of end up using those two phrases or terms rather interchangeably. Technically, they are different, but they're not different enough where I'm going to stress about it. Again, at the equivalence point, you have equal concentrations of H+ and OH- ions. This is where all of the acid has been reacted with the perfect amount of base so that we have equal concentrations of the two. Hopefully we've formed water, there's no extra ions left over, and we should have a neutralized solution. So again, H+ molarity and OH- molarity are equal to one another. Now, most students look at this and assume, okay, if there's equal concentrations of H+ and OH-, we must have neutralized it, we formed water, so our neutralized substance should always have a pH equal to 7. And I completely understand your thought process on that. Turns out there's a little bit more to it than just, okay, it's neutral, so it has to be at 7. We're talking about neutralized, so we've used up all of the H+ and all of the OH- ions, but we have conjugate acid-base pairs floating around in solution that will impact our equivalence points. Or I should say the pH at our equivalence point. Based on the pH we're expecting at the equivalence point, that's going to determine what type of indicator we want to use. So in your reference table, I think it's table M, you have a list of different indicators. This is not an exhaustive list of different indicators. There are more acid-base indicators out there, but these are the half dozen or so that the New York State Regents wants to focus on. In order to use this chart, we're going to look at the approximate range for color change. If we look at something like methyl orange, if we add this to a solution that has a pH lower than 3.1, we would see red. If the pH of the solution is above 4.4, the solution would be yellow, or the indicator would be yellow at that pH, in that pH range. In between, it's kind of a orangish color. So if we looked at something like bronchimal blue below a pH of 6, bronchimal blue is going to be yellow. Above 7.6, it would be blue. So if I'm anticipating a pretty neutral equivalence point, I would use an indicator like bronchimal blue. If I'm expecting an acidic equivalence point, I would use something like methyl orange in my titration. We'll kind of talk about what that means and reinforce it as we go. So choosing an indicator, question we're going to ask ourselves is, what is the pH of the equivalence point going to be? And what we mean by that is just, is it going to be acidic, basic, or neutral? As far as trying to pin a number to it, we're not going to stress. I'll leave that for AP chemistry and beyond. We just want to be able to determine, generally speaking, what is the relation going to be to a pH of 7. Acidic indicators are going to change colors at a low pH, basic at a high pH, and of course neutral is going to change colors around a pH of 7. And we'll see, this is a bronchimal blue. At different pHs, we see different colors. So this is, again, acidic. This is a more basic pH, and this is a neutral pH for bronchimal blue. Right. So we're going to look at a couple different titration curves and talk about kind of what we can expect as far as the pH around the equivalence point and which indicator would be appropriate to use in each case. So as we look at this titration curve, we assume that we've got like an Erlenmeyer flask with acid, and we're going to put base in our burette, and we're going to slowly add base to the acid. And we can see as we do that, pH starts to go up a little bit, happens pretty slowly. Then all of a sudden you end up with this like big inflection occurring, this huge change in pH over a very small volume. And our equivalence point is right in the middle of this big change in pH. And then as we continue adding base, the pH goes up and it kind of levels off again. Based on the pH at the equivalence point being roughly 7, we would say that this is a neutral equivalence point. In order to get a neutral equivalence point, we're going to neutralize a strong acid with a strong base. You can kind of like picture the acid and the base like arm wrestling one another. And if they are of equal strength, no one's going to win that arm wrestling match. We're going to end up with a neutral pH. Of course, during a titration, if you were able to see what's going on with the molecules and ions in solution, we of course don't have substances arm wrestling, but that might be a helpful visual when it comes to predicting equivalence points. Our equivalence point of a strong acid, strong base means the pH should be roughly 7. And if you take a look at table M, you want to pick an indicator that is going to change color over an equivalence, over a fairly neutral range. So like it's one color as an acid and then it's another color at a base. What two indicators kind of fit that description? Hopefully as you look, you see that litmus or bronchimal blue would be reasonable indicators. Both of them are one color in an acid and another color in a base. I would argue that bronchimal blue is a better choice just because it has a narrower range. Litmus is great for testing, is this acidic or basic? It's a little sloppy for a titration. All right, up next, we see an equivalence point below 7. So below 7, this is an acidic equivalence point. What combination of acid and base strength do you think led to an acidic equivalence point? The acid has kind of won this arm wrestling match, so maybe it's a strong acid and a weak base. And that is in fact what we would see. We end up with a pH less than 7 at the equivalence point. So even though the concentrations of H+ and OH- are equal, we still have a pH below 7. If you look at table M, 2 indicators could be used in this type of titration. What are they? Hopefully you're thinking methyl orange and bromcressyl green. Both of them change colors in an acidic pH range. 3.1 to 4.4 for methyl orange, 3.8 to 5.4 for bromcressyl green. All right, this one we have an equivalence point with a pH above 7. So this is our basic equivalence point. Hopefully you're kind of getting the hang of this, and you would predict that must be a strong base and a weak acid being used to neutralize one another. And our pH is going to be greater than 7 in the basic pH range. And if we needed to pick an indicator or 2 indicators that we could use for this type of titration, based on table M, you should be coming up with phenolphthalein and thymol blue. Both of them change color in a basic range. Phenolphthalein is going to be colorless, anything below 8, and pink, a pH greater than 9, and a similar range for thymol blue. So you might be thinking, okay, so we've looked at strong and strong, strong with weak. What happens if you've got weak with weak? This is the type of titration curve that you would expect to see for a weak acid and a weak base. Not a whole lot really going on there. We don't see that big change in pH the way we did for the other combinations. And it's for this reason that we don't titrate weak acids with weak bases. The change in pH is just too small to be useful. So don't run that sort of titration. It can be strong and strong, that's fine. Strong and weak, also okay. Weak and weak, very small change in pH. So it's not practical to do this in the lab. It'd be very difficult to determine the endpoint just because their pH range for most of our indicators is fairly large, and you're probably going to miss it. Let's talk about calculations that we would perform based on the data we collect during a titration. We're going to be using this formula, H+MaVa equals OH-MbVb. If we start thinking about what those different variables mean, we know that M stands for molarity, capital M. So M sub A is the molarity of the acid. M sub B is, of course, the molarity of the base. V is going to stand for volume. We can work in either milliliters or liters, but we need to be consistent. In other words, don't make the volume of the acid in liters and then calculate the volume of the base in milliliters. Use the same unit. The H plus and the OH minus have to do with how many ions are going to be produced when that acid or base dissociates. We can predict how many ions will be produced by looking at the subscript of the H in the acid's formula and the subscript of the OH in the base's formula. So this part requires a little bit of chemistry know-how, but hopefully by now dissociation equations have become something that you're very familiar and confident with. Let's go ahead and walk through a practice problem or two together. All right, so in your notes, you've got this problem. You're told that it takes 10 milliliters of a solution of barium hydroxide to neutralize 18.2 milliliters of 1.5 molar hydrochloric acid, and you're trying to find the molarity of the base. Okay, so there's a whole bunch of questions that I can ask you based on this type of problem. So we're going to kind of break them down into 3 different overall groups. We'll say reaction, so we can talk about the chemistry that's occurring. Calculation, we can actually go ahead in this case and solve for the molarity of the base. And titration. If I was to run this in the lab, how would I set this up? So hopefully this reaction section is review. Formula of the acid. Okay, I'm told I've got hydrochloric acid. That's probably an acid that you knew well before you came to our chemistry class. That's going to be HCl aqueous. And if you want to kind of ignore your phases, we can let that slide. Barium hydroxide. Barium is a group 2 metal. So we'd have BaOH2. Don't forget those parentheses around the hydroxide. We're going to run the reaction between hydrochloric acid and barium hydroxide. So in an acid-base neutralization, we know that one product will always be, hopefully no surprises, water. That's going to be in a liquid form. And the formula of the salts. Okay, so I'm going to take my barium 2+ and my chloride 1- ion. I can use the crisscross method and predict that I would make BaCl2. All right, so let's put those pieces together to write and balance our equation. I've got hydrochloric acid plus barium hydroxide yields water plus barium chloride. Forgot my phase of barium hydroxide. Sorry about that. So there's my equation. If I want to get this balanced, I'm going to need a 2 in front of the hydrochloric acid and a 2 in front of water. Right. So again, hopefully that is a review. Calculation. This is where we're going to have to put some new information in there. We know that we can find the concentration of, in this case, the base by applying the formula H+MaVa equals OH minus MbVb. So if we want to find the value of H+, we want to look at the subscript of hydrogen in the formula of the acid. So up here I've got hydrochloric acid as HCl. Every time one HCl breaks apart, I will produce one hydrogen ion. So the value of H is 1. I can do the same thing for hydroxide. Hydroxide and barium hydroxide has a subscript of 2, so every time one barium hydroxide breaks apart, I should be producing 2 hydroxides. Rookie mistake is to look at coefficients instead. Don't use the coefficients. This is just to balance the equation. It's not telling you how many hydrogen and hydroxide ions will be produced. Don't fall into that trap. Whoa, it's really zoomed in. Sorry, chemists. All right, so we can start plugging in what we know and we can solve. I've got 1 for the value of H+. You can ignore it if you want to, since it's not going to change our math. The molarity of the acid is 1.5 molar. The volume of the acid is 18.2 milliliters. Hydroxide has a value of 2. The molarity of the base is what you're trying to figure out. And the volume of the base is 10 milliliters. All right, so now it should just be plug and chug. And I've got 1.5 times 18.2 divided by 2 times 10, so divided by 20. Molarity of the base, what are we coming up with? I think technically we should have 3 sig figs. We'll give you some leeway with that, this unit. 1.37 molar. One thing I see a lot of is people don't put a unit at the end. You think you're telling me the molarity of the base is equal to 1.37, but on this side of the equal sign, m sub b is just a variable. You need your unit after your numerical value. So that's really the calculation that you should be able to solve using that formula. Hopefully, you'll have all but one of the variables and you can plug and chug. All right, and last but not least, we can think about how we would do this in the lab with a titration. Is the acid strong or weak? Hydrochloric acid, one of our 7 strong acids. What makes it strong? All strong acids dissociate completely. Base, barium hydroxide, also strong for the same reason. And it's a group 2 metal with hydroxide. I don't know why that keeps happening. Sorry about that. All right, will the endpoint be acidic, basic, or neutral? Endpoint, equivalence point. I've got a strong acid plus a strong base. So their strengths are equal to one another. They will effectively cancel each other out. So I should have a neutral equivalence point and a neutral endpoint. So I need to pick an indicator that is going to change pH as it goes from acid to base. So if I look back at table M and the possible indicators, hopefully I see that I've got bromthiamyl blue and litmus changing colors. Yeah, you could use litmus. I do think the better option is bromthiamyl blue. Again, just because it has that smaller range that it changes over, so you should get much cleaner looking titration data. Wow. I really like questions like this just because it does enable me to ask you so many different questions from a single problem, really. So definitely practice with this concept. You've got 5 practice problems to play around with on the next page. Definitely, make sure that you can answer these types of questions. You are guaranteed to see them on your unit test. All right, chemists, sorry that was a little bit of a long one today. Lots to cover, as I'm sure you gathered. Nice work with this. Keep practicing. Thank you for tuning in, and I hope you found this helpful.